Hello everyone. This tiny chip runs your washing machine, microwave, your car, and may even your toothbrush. It is called a microcontroller, the tiny brains inside billions of devices. In this video, I shall break down the fundamentals of microcontrollers, show you live demo, and explore real-world applications so you can see why they are one of the most important innovations of modern electronics. Did you know the chip running this heart monitor costs less than $5? A microcontroller is essentially a miniature computer, complete with peripherals, memory, and CPU. It is programmed for specific tasks. Once programmed, it can execute the task relentlessly. Microcontroller prices generally range between $1 to $10 per chip, subject to the volumes, maturity, and desired functionality. For example, low to mid-tier Atmel AVR and MSP430 series generally costs upwards of $1. STM32 and NXP LPC17XX series are high-end microcontrollers, costing average more than $5 per chip. Microcontrollers are available in two major styles. This one is called through-hole style, as it is soldered through the PCB. My personal favorite, it is human-friendly and easy to handle. However, most microcontrollers don't use this style because of larger footprint. This style is surface mount style and available in various formats. It is soldered to the surface of the PCB. It is not very human-friendly and hence not ideal for beginners. Sadly, most microcontrollers use this style because of the compact size. This is an example of microcontroller development board. A development board is a hardware ready to build embedded applications with minimal time. They come in handy with additional help such as debuggers, connectors, and real-life examples to give someone a hit-the-ground-running experience in microcontroller learning. This specific board is my personal favorite MSP430 low-power launchpad system based on MSP430 G2231 microcontroller. Let's review key household use cases. Take the example of humble remote control. It uses a simple low-power microcontroller-based system to detect button presses and generate infrared signals, which are then transmitted to the target device. Did you know even your favorite household device, a microwave oven, is equipped with a microcontroller, which controls the user interface and the power generated by the magnetron, which in turn cooks your food by intensely powerful microwave blast. You might be surprised that another super common household appliance, the washing machine or tumble dryer, relies on a microcontroller for precise timing and spin control. This is achieved through efficient and accurate speed regulation of AC induction motors. It also has humidity and temperature input sensors, which contribute data towards the washing cycle and spin control. Hello guys, here is a quick pop quiz. Please select most appropriate answer and let us know what you think in the comments section. Expanding our horizons, let's now explore the use of embedded systems in commercial and industrial applications. A typical mid-tier car contains 20 to 30 microcontrollers distributed across various subsystems. Components such as engine control, adaptive cruise control, and anti-lock braking systems, ABS, each have their own dedicated microcontroller, all coordinated by a central master controller. This setup serves as a beautiful example of a networked intelligent control system. Let's explore even further in our quest for microcontroller industrial applications. Were you aware that high-tech spacecrafts or space rovers, such as our beloved Mars rover, employ several microcontroller-based assemblies for life support, navigation, and communications? These sub-assemblies or components play a vital role in navigational support, life sustainability, and telemetric command and control functions, essential for the integrity of the spacecraft and any residents on board. This is a representation of a fundamental microcontroller architecture. Main CPU has an arithmetic and logic unit which performs basic functions such as multiply and add. Control and timing unit looks after the clock and other program control functions. Register memory is a super high-speed data memory available to the designer. Special function registers control and configure various peripherals on the microcontroller. Input and output system consists mainly of GPIO interfaces. Also available a very useful and important interface, JTAG or SWD, which is used to download and debug software into microcontrollers. Microcontrollers can only process digital information in ones and zeros. Binary 1 refers to as high or true. Similarly, 0 as low or false. All digital input or output actions must be interpreted as either 0 or 1. Any discussion of microcontrollers would be incomplete without the concept and considerations to GPIOs. GPIOs are magical little pins which are bidirectional. They can transfer data in or out. That is, GPIO can be configured depending on the need, either as digital input or output. All modern microcontrollers nowadays allow third configuration state analog. We shall now lay down fundamentals of a simple microcontroller or embedded system. Let's consider a lamp control system. It consists of a microcontroller, one output and one input. This is the layout of simple lamp control system. I am using a MSP430 Launchpad development board for this experiment. Notice that the lamp is activated only for the duration of push button switch. If you wish to, there could be many variations of the control logic, even using the exact same hardware. I have put together a simple demo, and this is the pictorial representation of the actual system. The 12 volts, 10 watts lamp is powered by external 12 volt supply, which is activated by the relay control. The relay is a cheap and cheerful 5 volts module triggered by the port 1.0 output. The push button on port 1.3 on board the Launchpad is used as input. I have prepared a video capture of lamp control system in action. Notice that the lamp is only switched on for the duration of push button press. Hello guys, here is a quick pop quiz. Please select most appropriate answer and let us know what you think in the comments section. In a nutshell, microprocessors are powerful CPU-only devices that require external components to function. A microcontroller, in contrast, is an amalgamation of CPU, external memory, and I/O interfaces all built in. That is also why it is often referred to as system on chip. As described earlier, microcontrollers are focused on dedicated tasks. Microprocessors, on the other hand, perform complex computational tasks such as design of plane propeller, complex computer gameplay execution, or mining new bitcoins. A good example of a microprocessor application is an Intel or AMD processor-based work or home PC, whereas a smartphone is an excellent example for microcontroller-based application. Microcontroller architecture is characterized by many attributes. One of the most important one is data bus width. Initial microcontrollers offered were mostly 8-bit architecture. Nowadays, market is littered with advanced 32-bit ARM microcontrollers. Bear in mind, higher the data bus width, better the performance or throughput of microcontroller is. Here are some popular microcontroller architectures available nowadays. PIC and AVR fall into low to middle tier consumer electronics, whereas ARM is used for more complex high-tier applications such as smartphones. MSP430 architecture has its own niche in ultra-low power consumer electronics, where it excels and outshines the competitors. In another interesting project, which I personally designed and delivered, a low-power MSP430 microcontroller is used to monitor temperature, humidity and pressure, and log data to an SD card with timestamp. The device is operated with 2 AA-sized batteries and was equipped to work on them for at least 2 years. Based on my favorite chip, Texas Instrument MSP430, ECG monitor is an ideal use case for a low-power yet reliable MCU deployment. This device collects heart rate from analog sensors and displays data over an LCD and transmits data over Bluetooth channel. In a more familiar use case, an Atmel processor is used to control the thermostat functions in a household environment. The inputs are temperature sensors and output is control signal to main unit. It provides a user interface to facilitate changing the set point. It connects to the main unit via the Wi-Fi protocol. In another use case, a smart electricity meter deploys high-performance 32-bit ARM Cortex microcontroller. The microcontroller is responsible for determining the user tariff, calculating and displaying energy usage, sensor interface and communication to the central hub. It also performs regular data backups on cloud. Thus, a smart meter is a sophisticated electronic household device, boasting high data throughput and strong real-time performance. Hello guys, here is a quick pop quiz. Please select most appropriate answer and let us know what you think in the comments section. Data bus width is one of the most important factors in determining the functional performance of a microcontroller. Legacy microcontrollers were mostly 8-bit system likes of fabled 8051 microcontroller. They were gradually outdated by the advent of 16-bit counterparts architectures from different vendors. Nowadays, 32-bit architectures are commonplace. For example, your smartphone employs a combination of a main processor and multiple microcontrollers. Most of them are 32-bit architectures. In my personal opinion, data bus width is by far the most important factor as far as the performance throughput is concerned. A performance throughput is defined as the amount of information which can be processed by a system. As demonstrated by this graphics, throughput is directly proportional to data bus width. I want to give you a basic idea on microcontroller specifications and what to look for. Here is a quick summary for a specific Texas Instruments MSP430 microcontroller. It's a 16-bit chip with 512 kilobyte memory and 64 kilobyte RAM with timers and comms features. Notice that I have highlighted the active and standby consumption currents, which for me personally would be the most desirable characteristic for this particular chip. I didn't care that much about clock, nor I normally do anyway while selecting a microcontroller chip, unless I am working on super high performance benchmarking project or a very specific requirement that puts constraints on data throughput. In last few slides, I shall discuss ideas and notions to help put you hopefully in the right direction. Microcontrollers are spectacular devices, and you can make amazing little projects with them. It can be confusing though to make a start as there are so many options. Arduino platform is, no question, heaven for starters. There is a library for almost everything. However, it does hide some crucial details from user. Exactly why it is so popular. I have mentioned few other options which can roadmap you onto a productive learning path. MSP430 is my personal favorite, but NXP32-bit Mbed series is very powerful. Scilabs have some interesting development boards. Crucially, all these IDEs or development tools I have mentioned are free to use, you just need to buy hardware. If you need help in selecting the right platform, please do let me know in the comment section. When selecting a microcontroller for a real-life project, many factors have to be considered. First and foremost, it has to be adequate for project interface and performance needs. However, there are many other secondary factors which play an important part in the longevity of the project. Cost, availability, power consumption are just some of them. Make no mistake, choosing the right microcontroller development platform is one of the most important decisions in a project.